So thank you, everyone, for being here. So I'm Fanny Henriet, and I'm going to present a joint work with Renaud Coulon, who's at the University of Melbourne, and Leo Heitzman, who is a PhD student at PSC, and who is going to be visiting this winter in Marseille. So it's a paper about oil, and it's entitled, as Ewan said, Bad Oil, Worse Oil, and Carbon Misallocation. So in order to understand what we do in this paper, you have to know a few things about oil. So the starting point of the paper is the fact that there are differences in CO2 equivalent emissions per barrel, depending on the oil you consider. So for instance, if you extract 1 barrel of oil in the Ghawar field, which is the biggest field in Saudi Arabia, it's much less polluting than if you extract 1 barrel of oil, say, in bitumen sands in Canada. So there are these differences. So 1 barrel of oil can emit more or less GHG emissions, so greenhouse gases emissions, depending on the oil you consider. And these differences, they mostly originate from the upstream sector, that is to say, from the extraction sector. So this is the first thing. The second point is that there is too much oil. So what do I mean by there is too much oil? It's that if we want to keep the temperature increase below 1.5 degrees or even 2 degrees, it must be the case that we let a huge part of the oil reserves that we know under the ground. So of course, if you take these 2 points together, it means that by choosing to extract rather the clean oil rather than the dirty oil, you can have the same total supply and have less greenhouse gases in the atmosphere. So you're going to have lower cumulative emissions if clean oil is extracted instead of dirty oil. And somehow that is what maybe would happen if there was proper carbon pricing. Okay, in this case, you would have an incentive to extract rather the clean oil because it would be less expensive for you. But we know that carbon is mispriced, and it's particularly true for the emissions from the extraction sectors that are not priced at all. So if you take now these 3 things, you understand that you're going to have carbon misallocation, what we call carbon misallocation, with dirty oil being extracted instead of clean oil. Of course, this is not the only source of inefficiency in the oil sector, because you also have expensive oil and cheap oil, and you also have expensive oil that is extracted, whereas you could extract cheaper oil. And this is partly due to market power. What we do in this paper is that we quantify the carbon misallocation since 1992. So why 1992? It's because it's the Rio Summit. So it means that there was information about the climate change, and everyone was aware that there was this big externality. So what I mean by carbon misallocation is we quantify the extra emissions from wrong field level production, given an aggregate supply. So we take the total supply as given since 1992, and we look at by how much we could have decreased CO2 emission, greenhouse gases emission, by choosing from the right field. So it's really super simple. So we identify the deposit that should have been more exploited and those less so. And so it allows us to match with what we call countries' ecological debt. So some countries extracted too much oil, and some countries not enough for a given supply.
Supply is not given. It's been given since 1982.
No. So we take as given what we look at as really for a given total supply by how much we could have decreased emission. Of course, if we had a price on CO2, then maybe the demand would have been lower. Is it what you're saying?
Well, it's just that since 1982, the supply of oil in the world has not been given. So I mean, so you are going to take some benchmark somewhere. which benchmark are you going to take as a supply? Because you want to, I'm not sure if you have a moving.
Okay, so maybe the total supply is not the right way to say it. So we're gonna take as given for given consumption each year, but we're not gonna model it. So maybe it's gonna become clearer when we disentangle the misallocation in CO2 emission that can be attributed to market power or to the absence of a tax on CO2 emissions. So this is for the past, and for the future, we examine the distribution of stranded oil deposits. So what I mean by stranded oil deposit are those oil reserves that have to stay under the ground if we want to keep the temperature increase below 2 degrees. Taking into account differences in extraction cost and carbon intensities. And so to do so, we use rich field-level data on deposit extraction cost, carbon intensity, and size of the reserves. Yes?
Right. Sorry. So oil extraction has some important political economy aspects.
Yeah.
And as you know, some historical producers of oil are autocratic countries.
Yeah.
And so will you take this into account in any way? Or?
So at some point, we're going to look at fixing each country production by how much we could have still decreased CO2 emissions. So saying, OK, so we keep each production as given, so that there is no impact on energy security, for instance, or so we take all this as given.
Okay. So how far can you get if you stay within, if you fix it within
we can quite far.
Okay.
Because there are actually large differences within countries.
Thank you.
So I go on. So and how we're going to do what we want to do, we are going to compare the historic supply, so that we observe, to counterfactual supply that we built. Okay, with the same aggregate supply path. Okay, so I don't know if it answers somehow your question. So just to preview the main findings, we find that if we look at the past, so 1992, 2018, we found that what we call inefficient emissions are at least 10.1 gigaton of CO2 with aggregate supply and change. So this is really a lower bound, and this is between 4 and 16%, depending on which IPCC report you look at, of total remaining carbon budget. The cost is about $2 trillion US, with the social cost of carbon quite high, but that is consistent with the future decrease with the IPCC report, at least. If we look at our ecological depths, we find that Saudi Arabia or Kuwait should have increased their extraction, and that some countries, a lot of countries actually extracted too much of their oil. For instance, Venezuela, Canada, or China. And interestingly, the countries that signed the Kyoto Protocol, countries that are in Annex B of the Kyoto Protocol, meaning that they committed themselves to decrease their emissions, they over-extracted oil by 66%. Another important result is that we find that carbon misallocation is really distinct from private cost misallocation. We could have expected that those countries that have high costs, they are also more polluting, and they because of market powers, the low-cost countries like Saudi Arabia decreased their production, allowing high-cost country to enter into the market, and this would have given rise to more pollution. Actually, we find that by solving private cost misallocation, we're not able to solve at the same time carbon misallocation. So the cost-effective supply that would ignore pollution. So if we just remove we just make the cheapest oil extract. Cost-effective supply brings only 10% of the emission reductions of the optimal supply. So we have a way to compute the misallocation attributable to OPEX market power, which is 20% of total misallocation, where carbon mispricing can be, we can attribute 20 to 25% of total misallocation. So that was for the past. Now looking toward the future, yeah. It would not solve private cost misallocation, right? Because there is market power there.
But it doesn't sum to one.
No, because there's some part of the misallocation that are linked to energy security or to other things. So we are working on this unexplained source of misallocation. That's what we're doing right now. Yeah. Okay. So if we look at the future, we find that there is still room to have a good extraction. So if we compare the optimal supply structure as of now to the cost-effective supply that ignores pollutions, and we can save 7.6 gigaton of CO2, even while the future demand is projected to be very low because of we take a scenario of 2 degrees. We also find a very unequal distribution of stranded oil reserves. So say again, if you take Kuwait, only 26% of the reserves have to stay into the ground, whereas in Canada, it's almost all the reserves. Okay, no question? I can go on. Okay. So just to why we do that, so we don't say that we should not decrease decrease the demand for oil or the total quantity of oil that is consumed. We only say that, for instance, the transport sector is really difficult to decarbonize, so it's important to take into account also the supply and not only the structure of the supply and not only the decrease in total consumption. This is an important lever to decrease emissions. Plus, we think that it's important to understand the distribution of stranded reserves and what are the differences in oil field that should be taken into account to decide of which are the oil we want to consume or not. For the literature, we built mainly on a paper by John Asker and his co-author. They look at the inefficiencies in the oil market that are due to OPEX market power. In our paper, we have pollution, and importantly, we take into account the fact that oil is abundant if we want to stay below the 2 degrees limit. And we show that the selection of deposit to exploit is key. Okay, so there is also this paper about imperfect competition in the oil market and the climate, where they have both imperfect competition and environmental damages. But it's a theory paper, it's quite different. So I'm going to go fast here. So for the methodology, so we compare deposit level counterfactual production and realized production post-1992. So for the counterfactual, we minimize a discounted social cost in which there is the environmental damage. So the total social cost of oil extraction under various constraints, and assuming again that the annual demands are satisfied. That is to say, in the counterfactual, in our data, the total production is the same. Okay. So the data we need to do that is at the deposit level, we need the extraction cost, the carbon intensity, past productions, and the reserves. And we need each year the global annual demands. Yes?
At the deposit level, the extraction cost is not constant, right? There is a dynamic profile.
Yeah. So actually, we we take a constant marginal cost here. We also have other version in which we have increasing extraction costs. So we have a constant extraction cost, but we have a limit on the quantity that you can extract each year. You have capacity. But we also have a version in which we have increasing extraction costs. And actually, we have a version in which we estimate the extraction cost on the data, and we have different bins of costs.
The extraction cost is stock dependent.
Is?
It's stock dependent, the extraction.
That's not clear at the well level, actually. So, yeah.
So you don't have dynamics of the stocks?
No. Of each field, of each well, no. So if you look at the well level, actually, so we are so we don't find that it's stock dependent, but we can talk about that if you want.
So another question is that the data on reserves are notorious to be very bad.
Mm.
You know that all the reserves that are announced by the OPEC members are unreliable.
Okay, so these are the Restart data, which are professional data at the field level. So what we take is that we take for reserves the sum of past production plus the reserves at date 2019, knowing that in 2019, that's not clear that the OPEC member say that they have too low reserve, that the reserves are lower than what they actually are. And we also have a version in which we take at each date the reserves that are given by the firms, by each firm at each year. Okay, so we have two different definitions of reserves for that. Okay. Okay, so we use this Restart proprietary database, which gathers the upstream data on all significant oil fields from 1970 to 2018. So there are plenty of data on production, cost, field location, ownership, oil and reservoir characteristics. But there is no carbon intensity in this database. So in order to have carbon intensity at the field level, we use two state-of-the-art models for carbon intensity estimation. So there is this public data. There are these public data of 1,000 fields in which there are all the big fields, but not only. From a recent paper by Masnadi and his co-author in Science. And we match these fields with those in our database, and we use the info that we have in our database, in the Restart database, to explain the carbon intensity of the field for which we know the carbon intensity. So the variables that are important are the variables we know are important. That is to say, the oil type. So do you have, regular oil or extra heavy oil, etc. The gas to oil ratio. So it's important because when you have a lot of gas in your reservoirs, and a lot of gas is going to go out when you extract the oil, and it's really polluting. So it's flaring and venting. Yeah.
Data on like these kind of oil, like shale oil or sand oil.
Yeah.
You don't have any real reservoir there. You have.
Yeah.
It knows really how much oil there is. If you extract it from.
You mean the reserves?
Yeah, the reserves, or even what you call here the reservoir.
Okay, so we have the type of oil. So for shale oil, we know that the carbon intensity of this oil, that's going to depend on the quantity that is flared.
You know how much there is.
We have data on reserve. So you don't believe in the reserve of... okay, so we could...
Oh, I don't know.
No, maybe. So we can find that maybe they are underestimated. So we could take that into account. But actually, they are stranded because they are very expensive. And so it would be, actually, we're not using on the reserves. So the constraint on reserves is not really binding anyway for these reserves. Okay. So whether it's an onshore or offshore field, and we use satellite data for flaring, and so flaring is the gas that goes out when you extract oil. And so we use this model to predict the carbon intensity for the other fields for which we don't have the data directly of carbon intensity. We do the same for refining emissions. So to give you some insight, so the more polluting sector in oil is, of course, combustion, right? It's the downstream emission when you you drive your car and you burn your gasoline, right? This is much more polluting. But the variance in the emission comes much more from the extraction sector, from the upstream sector. So that is why we focus on the upstream sector. Not sure that you can really see what is here, but so these are different types of oil. So for instance, you have bitumen here, and you're going to have light oil here or regular oil here. And you see that the carbon intensity is going to depend on the type of oil, not surprisingly. Okay? But still, within each type of oil, you have differences in carbon intensities. This is for different countries. So here you have Saudi Arabia. Here you have Canada. So you see that here again, you have differences depending on the country you look at. But within each country, you also have differences in CO2 emissions, in greenhouse gases emissions. So you have some fields that are very polluting and some fields that are less polluting. So for instance, Canada, you don't have only bitumen in Canada. You also have regular oil. In gray, you have the countries from OPEC, and in black, you have the countries outside OPEC. So if you wanted to only decrease emission, if that was your only objective, then you would draw the supply curve of and you would only take those fields that have the lower carbon intensity, right? And then you see that you wouldn't extract bitumen in red, for instance, here. Okay, but you see that you would extract some regular oil, but you would let some regular oil under the ground. Okay. Now, if you wanted to only minimize the total cost, you would choose to extract only those oil that have the lowest costs, right? And you would let under the ground the oil that have a higher cost, and so you see that here again you would let bitumen in red, most of the bitumen under the ground, right? But actually, if you did that, so here you see that this is the point estimate of the average, actually, carbon intensity of this oil that you would extract. And this is the average carbon intensity of the oil that you would let under the ground. And this is the 10th and the 90th percentile. So you see that actually there are differences in carbon intensities within the cheapest and also within the more expensive oil.
So you don't have the shale oil here?
Actually, shale oil, it's a regular oil. It's a light oil.
Okay. I thought it was more,
but we have,
it was dirtier in terms of carbon.
Actually,
okay,
so,
it's not.
no, bitumen is really dirty.
Yeah.
Shale oil, it has, it takes a lot of, it's not that, in terms of greenhouse gases emissions, that's not that polluting.
I see.
Okay, but there are other externalities that are associated to shale oil extraction. Okay. So it's just to say that there is a low correlation between carbon intensity and extraction costs. So now that we have all this information, we can build the optimal counterfactual. So we take a carbon cost. Theta D is going to be the carbon intensity in field D. CD is going to be the private extraction cost. So we're going to take it as a constant marginal extraction cost in the main exercise. And we're going to minimize the total cost, social cost of extraction under the constraint that at each date we have to produce at least what was demanded this year. That the sum of what you extract from field D has to be lower than the reserve of this field, and that you have a constraint on the capacity on the total quantity that you can extract each year. And you have the social cost of carbon that is consistent with a carbon budget approach. So meaning that the total cumulative emission has to stay below some threshold. So that is what we built. So we could compare the optimal production as computed here to what was observed only between 1992 and 2018. But actually, that would overestimate the gain from the optimal supply, because, of course, when you use a very good resource, not polluting resource at all, in your counterfactual between 1992 and 2018, this means that you cannot use it anymore in the future. Okay? Whereas in the observed, in reality, it's still here in 2018. So we have to take into account the fact that there is an opportunity cost of using the very good reserves in the counterfactual, in the past counterfactual. So we need a future to take that into account. So we built a future where we have an exogenous demand, and we have two futures, either a cost-effective supply or an optimal future. And what we're going to do is to compare the optimal path from now until the end of oil in 2050 with the observed, with a future that is, in most cases, which is an optimal future from now. So we assume that from now we are going to do the best that we can do until the end of oil. Okay. And so we're going to compare the counterfactual to this observed plus future. Okay, this is clear for everybody? Okay. So as I said in the beginning, when we look at the difference between the past misallocation, between the observed plus the clean future and the optimal counterfactual, so this is a lower bound that is really the emissions that are lost, right? So even if from now we do the best as we can, we are not going to be able to decrease we lose 10 points because of the past. We lose 10 gigatons of CO2, and it's robust to very different social cost of carbon. If we do only from 1992 to 2018, as I said before, so without taking into account the opportunity cost, it's more than that. It's 15 gigatons of CO2. Now, what can still be changed in the future? We can still see differences between the different features in which we have carbon pricing or not. And the order of magnitude is still quite large because it's 7.6 gigatons of CO2. Again, the minimal private cost supply generates only 10% of the optimal abatement. This leads us to conclude that carbon misallocation and private cost inefficiency are distinct. Okay. So here in this table, what you have is here you have baseline production, in percentage of global production. So Saudi Arabia, for the period 1992 to 2018, is the biggest producer, and the production amounts to 13% of total production. And you see that in this column, we compute the production of each country in our counterfactual as a percentage of the observed. Okay? So for instance, no, actually, it's the increase in production. So the increase in production compared to today of Saudi Arabia, if in the optimal counterfactual, is 179%. Okay, so in fact, in this counterfactual, you see that Saudi Arabia should have increased a lot its production, and Russia should have decreased, the US as well, etc., etc. So you see that this means that this entails huge reallocation between countries of production. So this is a problem. So you see that so it's significant production variation across countries. So as we know, international transfers and compensation are difficult. So we redo the exercise, but under feasibility constraints, what we call feasibility constraints. So one of it is that annual production in each OPEC country has to match the observed production in the past. So this is a way of saying, well, we cannot decrease or increase the OPEC production. Say in each country they decide how much they produce. Energy security constraints. So we say that maybe it is the case that actually, if you are an oil producer, you want at least to produce for your country because you don't have any don't have any energy security problem if you do that. So we impose that countries' counterfactual annual production has to be higher than countries' consumption. And even the last one is that annual production in each country match baselines one. That is to say, we constrain the production of each country to be equal to what it was in the past in reality. We find that there are still large emission reduction between 9 and 11 gigatons of CO2. So this means that even with this constraint, you're able to reshuffle oil production so that you decrease a lot emissions. So this is because there is important within-country variation in carbon intensity, and this argues, in a sense, in favor of political feasibility of supply recomposition. Yeah.
So somehow, if you take into account in the various scenarios the social cost of production, you will create somehow patterns of specialization which were not existent before, and you put constraint on these patterns of specialization. But the question is, should we expect what was true in the past to hold in the future, especially with respect to allocation within OPEC? Maybe one country that will exploit its comparative advantage, like Saudi Arabia, might decide just to produce everything it can. So my question is, I guess, is more about the constraint you put and how you can evaluate whether this constraint will hold in a future that is very different from the past.
Yeah, so what you're saying is in the future, what kind of constraint do we put on countries, right? So that's a good question. So we have actually several scenarios, but one in which the OPEC countries remain with the same share as in the past. But you're right that maybe because all these countries know that their oil is going to be stranded, they are going to want to get rid of the oil as soon as they can. But then that would lead to perfectly competitive supply. And if you look at the perfectly competitive supply and compared with the optimal supply, you still have this 7.6 gigaton of CO2. So that would work. And still, the fact that there is within-country differences in carbon intensity tells you something about the fact that no matter what are the incentives of the country, if it's not linked with the carbon intensity, we can stick to the production that you have in mind. Another question? Okay. So in this graph, what you have here are in the x-axis are the gains in private costs, and in the y-axis the environmental gains. And in green, you have all the cases where you have carbon prices, and in blue, the cases where you don't have carbon prices. So you see that when you don't have carbon prices, you can have very high gains, right? But you're never going to have big environmental gains. Okay, and you see that even with constraint, you're going to decrease a lot the gains in private costs with constraint on production by country, but you're not going to decrease a lot the environmental gain. This is for the whole period, so this is not 10 because it's 10 plus for the future. Okay. Now, if you look at the future, you can look at the country's stranded reserves in percentage of 2019 reserves. So here again, you see that only 28% of Saudi Arabia's reserves are stranded, whereas, for instance, 84% of Russian reserves are stranded. And for Canada, it's almost all the reserves, and for the UK as well. Okay. So actually, I was faster than I expected. So we have plenty of sensitivity analysis. So we have end of the oil era that is in 2060 and 2080 instead of 2050. We change the interest rate. We loosen and tighten the extractive capacity constraint. We have alternative carbon intensity measures. We have imperfect substitution between oil deposits as well. What we are doing now is to account for supply disruption, say war, to introduce wedges to rationalize the observed extraction path as the competitive decentralized path. So, yeah, what's puzzling in what we have is that we're not able to explain 100% of the misallocation that is observed. Okay, so part of the misallocation we can attribute it to carbon mispricing. Part of the misallocation we can attribute it to OPEC market power. How we do that is by setting all the production of each country that is in OPEC and compare with the optimal counterfactual. And so we are able to decompose that, but there is part of the misallocation that we are not able to explain. Okay, and so that is what we are trying to do. So to find what is wrong, what are the either the externality or the mismeasurement in cost, or that explain why we are not able to rationalize fully the observed supply. So that is why we account for supply disruption, and we account for taxes, and we account for dependencies between the different deposits, etc., etc. What's important is that so any regulation of downstream emissions that treats all the crude similarly misses out large mitigation opportunities. So if you only rely on demand reductions, then you're going to miss some part of the story. Second point, there are still large gains from supply recomposition now, but still in the future. Okay, so even now there are still differences between what we would do in an optimal world and what's going to be done. And the environment policy is different from a pro-competition policy in which you would only take the least cost deposits. You would extract from the least cost deposits. So for implementation, of course, this is not that easy. So the easy answer is that we need carbon pricing in the oil industry. But not that easy to have an oil price at the world level. We all know that. In part because there would be strong distributional impacts with some countries with very large stranded assets, and that would make acceptance uneasy. So another way would be to fix country production and by region, and to put within region carbon prices with some compensation. Another approach would be a supply-side approach, a la Arstat, meaning that the rich country could buy all the bitumen extra heavy or heavy oil deposits, and those with extreme flaring to oil ratio, just to keep these oil under the ground. And then let the market do the job. So to conclude, a little bit in advance. So again, large emission reduction from supply recomposition. There is evidence of large ecological debt of dirty oil owner, but in particular those countries that signed the Annex B, and there are still large gains, so we can still do something even by constraining each country production. And that's it. Thank you for your attention.
We have time for questions. Do we have questions from the audience? Yes.
Thanks for the talk, very interesting. If I understood well, so to measure the CO2 savings you can afford in the future, you had to take into account a 2-degree scenario, is that right?
Yeah.
And so what happens if you change this scenario and you take a 3.5 or even higher temperature scenario?
So if you have a different scenario, you have two effects. So the first one is that you use more oil. So actually you can have more difference if you in cumulative emission if you have more oil. And the other effect is that, of course, if you burn all the oil at the end, this is the same. You're going to have the same emission in both scenarios, the same cumulative emission. So actually, with the what we find is that if we increase, if we increase a little bit more the production in the future, the first effect dominates until something like, I don't remember exactly, but even if the end of oil is in 2100, and if it's twice the scenario that we have, we even have larger gains than what we have in the basic scenario, in the baseline scenario. So still, it's yeah. But of course, if you exhaust all the oil, then you're going to have the same quantity of emission in all these scenarios.
Of course, but I was wondering whether if you exhaust all regular oil with a scenario at 3.5, I don't know, and then you have to go with full stranded oil and and what was the result that you
Yeah, actually, you don't exhaust all regular oil in the scenario that we have, but yeah, still you can have even bigger gain. So even if you don't believe in the 2 degrees scenario, actually, it's you should do it. You should choose to extract from the clean oil because you're going to have higher decrease in emission.
But just a following question, but if you take a higher temperature scenario, then does it change something with the exercise you make when you keep the extraction constant across countries?
Yeah, we have. Yeah, actually, there are large heterogeneity within country as far as emission are concerned, depending on the field you're looking at, and so this is partly due to the flaring that is really different between the different.
Yes. Thank you very much. So a bit linked to the previous question. So I think you showed the one table with two options. So one was the clean future scenario, and then the other one, I guess, was if you minimize the cost of extraction. And so and then you had the variation between countries of the production, and it seemed that it was very consistent, the two of them.
Yeah.
Whereas you said that I think if you minimize cost of extraction, it only accounts for 10% of the decrease in the emission, which means that actually, indeed, there is a lot happening within countries.
Yeah.
But really a lot. I mean, it's like almost the same evolution for each line.
Yeah. So actually, what's happening is the costs are really different. The extraction costs are really different between countries. So you're always going to take more oil from some countries, and then within countries you're going to reallocate between the dirty and the clean one. And this is for the future. But if you look at the at the past, it's slightly different. If you look at the minimal extraction cost and the optimal. But yeah, for the future, the differences in costs, they are more important than the differences.
Huge carbon pricing.
Yeah, but actually our carbon pricing is quite high. No, not necessarily, because you have, for a given level of prices. So this is when you, so basically what's happening here is that you're gonna take all the oil from Saudi Arabia, and you're not gonna take any oil from outside. And then in Saudi Arabia, you're gonna choose within between different Saudian oil. And so if the difference within Saudi Arabia is not that big between the extraction costs, a tax of $200 per ton of CO2 is going to do the job. But it's quite a high price, actually, for sure.
Yeah, so I mean, what is good about the result is that it will be easier to implement than the other way around. I mean, so yeah, what you're promoting is that we should transfer oil production to Saudi Arabia and the Gulf countries and remove it from Canada and Norway, and so
exactly.
It's easier to do it this way than the other way around, right? Obviously. But no, I had a question about the uncertainty here. How will your calculation stand if I allow for a deep uncertainty with respect to the evolution of the reserve? Let's say we are moving everything to Saudi Arabia, but then we realize suddenly that they don't have that much oil as they were claiming. Then we have to re-switch it again to somewhere else. I mean, so the uncertainty, the constraint, I mean, I guess it will be important to put some uncertainty into that.
So we have this version. Well, this is one way, but maybe there is someone that is better, something that is better, someone that has a better idea. So we assume that the data that we have each year. So at each year we have the proven reserves. That is to say, there's a reserve that people say they have, and we are taking these proven reserves as their reserves. So we do as if they optimize, knowing that this is their reserve. And then the next year, we have different proven reserves, and we redo the optimization, etc. So this is a way to see whether the information that we have at some date has an impact on if it changes, because we have changes in proven reserves. And so we're working on that. So the results are not quite here, but it seems to work as well. So still, even with some uncertainty on the reserves, you can still have you can still choose to decrease your emissions.
Yes, but if the uncertainty was different according to the different kind of oil, then this could mitigate. I mean, I guess it will not be the case because I don't know anything about oil, but my conjecture will be that it's easier to evaluate, let's say, the reserve in a field, in a given well, in Saudi Arabia, than to estimate, the sand oil in Canada or these. It's much more difficult. But I mean,
what's true is that each year you have an increase in some reserves. So that's what we are trying to do. We are also trying to. One way also is to consider that all the reserves that are not known at some point in time. So in 1992, we don't know about the reserves in Canada. They are not discovered yet. And it changes the path of extraction. So we take that into account also, and we still have robust results. Yes.
So you said at the beginning that upstream, the upstream sector is the one that is more polluting, right? And
it's not more polluting. It's where the variance lie between the different barrels.
The downstream has a higher variance, but the upstream has the highest average.
The other way around.
The other way around. Okay. But so I was wondering. So if you shift supply to Saudi Arabia, for example, then you have to transport that in other countries, which means that you're polluting and continue. Yeah. So do you account for that? I don't know whether it is relevant, but just.
Yeah. So actually, the transport is really a small part of the pollution that is related to oil. Even if you consider the upstream sector, it's really small. And one answer would be actually when we fix each country production. That answers for that, right? Because then you have the same transportation emissions. But you're right that we can compute more an extra emission that is, or less emission actually, that are due to the fact that you have to change transportation route. But actually, this is small, very small, in the whole process. Yeah.
So if I understand well, after your feasibility constraint, you show that even within countries, we can do better in terms of allocation, and it can be also less costly because the extraction cost will be lower, if I understand well. So the question is, why Saudi Arabia and the other countries don't do that, and whether or not they're going to win on the long term with this reallocation, because the extraction cost is lower, or whether or not we have to rely mostly on the tax, like it has been said before.
Yeah, actually, so Saudi Arabia, by decreasing their production, they have an impact on the price, on the final price, right? So actually, that's not sure that they would be winning by. They would have been, in the past, if they had produced more. Then the price would have been lower, and then they would have less profit, right? Not sure that so why don't they decrease their production? Actually, why don't they increase their production? Actually, it's to keep the price high. But that raises the question of how can we make them produce more instead of Canada, say?
Yes, because also if you decrease the extraction cost, they can expect to have a higher margin on when they sell the oils. But the question is whether there is a sunk cost of reallocating the production even within the countries, you know, to like increase some like the capacity of some extraction post where it's less costly, and to decrease other places.
Yeah. So that is why we have this. So it could be the case that so there is a reason why, right? They produced from one field rather than another. So it can be local externality, like, I don't know, employment or, you know, local political constraints. It could be that historically, once you invested in one field, you have fixed costs. So what we are doing now is really to look more deeply into this question and to look at whether when you have fixed costs in the beginning and then lower marginal costs. So we have a version in which we removed all the upfront costs, and we say these are sunk costs and they are paid in both scenarios, and we are able to see whether we are able to rationalize more what we see, but there are still a large part of there is still so we are able to decrease a little bit what we can't explain, but we're still working on it. Yeah.
Okay, I think it concludes today's session. Just to add, Fanny will be with us for a year, and next seminar will be next week, same room, same hour. Thank you.
Thank you.